Has anybody in this room ever seen a lecture of mine on video or somewhere? Excellent. Is there anybody in this room who has never seen a lecture of mine? I'm happy to see that. The others, you can go home. You will be able to lip sync me. 3 prisoners were sentenced to death. One of them French, one of them German, one of them British. What is your last wish? They ask the French guy. He says, a bottle of exquisite Chateau Lafite. What is your last wish? They ask the German guy. He says, I want to give a speech. What is your last wish? They ask the British guy. He says, I want to get shot before the German starts his speech. Unfortunately for you guys, it is too late now. I'm here to speak about the grand theme of the 21st century, which is the rise of artificial intelligence, which is going to transform every single aspect of our civilization. Before I do that, oh, that's the way how you pronounce my name if you're not from I want to think back of the previous century. What was the most important thing in the previous century? Some people think maybe the Second World War, but no, there was something much bigger than that. It was an invention, and in 1999, the journal Nature made a list of the most important events or inventions of the 20th century. And number 1, of course, was the one that made the 20th century stand out among all centuries in the history of mankind through the population explosion, which went from 1.6 billion people in 1900 to soon 10 billion. And that single invention that drove that thing was the Haber process, invented in 1908. Under high temperature and high pressure, you extract nitrogen from thin air to make artificial fertilizer. And without that, 4 billion people could not exist. So we would have at most 4 billion people on this planet and not 8 billion. And soon 2 out of 3 people will existentially depend on this one invention, which is still used to make 500 million tons of artificial fertilizer every single year. Nothing, no other invention had comparable impact. Billions and billions and billions of people would never have lived without that. But the AI explosion in the current century is going to be even much more dramatic. There we won't speak about small factors such as 4 or 10 or something, but trillions of trillions. And much of that is driven by an old trend in computing, which basically says that every 5 years, computers get 10 times cheaper. This is a trend which is much older than Moore's law. Moore's law says every 18 months you have twice as many transistors on a chip. But even long before there were chips, there already was this law, and it dates back at least to 1941 when Konrad Zuse built the first working program-controlled computer. And since then we have experienced 75 years, and roughly every 5 years another factor of 10. So now we are 10 to the 15 times cheaper in computational terms than 75 years ago. And now for the first time we are in the realm of small animal brains. Not yet human brains, but small animal brains. And it shows. Now this trend was obvious already in the 70s and 80s when I was a young man, and there I decided to devote my life to building something that is smarter than myself such that I can retire. And since then, all the decades of work were really just about that. And my diploma thesis of 1987, that's the picture, the cover that I drew there for my diploma thesis, already illustrates that little dream. Back then, the diploma thesis was about a learning algorithm, which not only learns to improve in a certain given domain, but which also is self-referential and learns to improve the learning algorithm itself, and learns to improve the way the learning algorithm improves and stuff like that. Meta-learning, because I figured once you understand how to build a system that not only is limited to a certain particular learning domain, but can adapt to any situation, then I'm done. So that was what it was all about. Now, the best way of computing in this universe is not a traditional computer, but it is something that is a lot like the human brain, because physics dictates that in this three-dimensional universe, you want to compute with a parallel processor, where you have lots of processors in a very small volume, connected through many short wires and few long wires. Many short wires, few long wires to minimize communication costs. So very much like a recurrent neural network of the type that we have in here. Does anybody in this room know anything about artificial neural networks? Okay, quite a few. Does anybody in this room not know anything about artificial neural networks? I notice that we have a third group. Who maybe didn't understand the question. Deep learning, this new buzzword, is just a new name for an old hat, namely these artificial neural networks, which in the beginning were feed-forward. So many of you know what that is. So you have these input neurons, and then you have a first layer of neurons, and each of these little neurons just computes the weighted sum of the activations of the numbers that you find there at the input units, where you can, for example, have images coming in and stuff like that. And then you get a second layer of activations, and they feed their own values into the next layer of neurons and so on. And then you get deeper and deeper. And in our business, in this business of deep learning, depth means power. Because with deep networks, you can do many things that you cannot do with shallow networks. And this has been realized for a long time. So all this deep learning, sometimes some people, some journalists even, they get their information from blogs in Silicon Valley, and they seem to think that is a recent thing. But no, this deep learning stuff goes back at least 50 years. The first guy, the father of our field in deep learning, that was a mathematician from the Ukraine. And there in the Ukraine in 1965, together with LAPA, he published the very first multi-layer perceptron, which really learned, which was much more powerful than single-layer perceptrons, which some of you may know. So these are just very shallow networks where you have only one layer. But he had already 8 layers or something like that in the 60s and early 70s. And he had a working method for doing that. The father of our field, the father of deep learning, e-learning. Now, what he didn't do back then, he didn't use a method called backpropagation to train that. Who knows about backpropagation? Who knows what that is? Okay. Who doesn't know what is backpropagation? Mm-hmm. Who is already asleep? Yeah. Backpropagation also was invented around the time when Ivan Nickel did his thing. And the modern version of backpropagation was invented and published by this guy, Liinaima, Finnish master student. Master student, in 1970 he published backpropagation code. And that was in his master thesis. 1970, what is backpropagation? Well, you have a graph of connected nodes, and they are all differentiable, and at the output of this graph, you have a function coming out, which is a function of the inputs, but also of all these parameters in the system, all the weights, the connection strengths, for example, or other differentiable things. And then there's a difference between what the output should have said and what it really said. You call that the error. Now, you can compute backwards for every parameter in the system the contribution of that parameter to the error. So using something which is called gradient descent, and backpropagation is just an efficient way of computing gradient information backwards. through deep multi-layer systems. And that's what Linnaeus published in 1970. In 1970, when computers were 1 million times faster for the same price than when Zuse did the first general purpose computer, but 1 billion times slower than today. And back then in 1970, really not many people had access to computers. Nevertheless, he published, he open sourced his Fortran code. Back then, people wrote in Fortran. And so even back then, there was an open source movement, if you will, and he was one of the protagonists. And then later, Paul Werbers was the first who applied that to neural networks, because Linnaeus, he formulated it as a general way of computing backwards these error signals, and the application to neural networks is one of many possible applications. That was done by Paul Werbers in 1982 for the first time. Now, the deepest of all networks, they are, and so here, see here, Linnaeus, so you see, Linnaeus apparently did that around the time when color photography was invented. Building on even earlier work by control theorists in the early 60s, Kelly, Bryson, and Dreyfus. The deepest of all networks are the recurrent neural networks. The recurrent networks are general purpose computers, because there you have feedback connections, and with feedback connections like that, you can compute anything that is computable. Because you can implement the laptop, this CPU of this laptop, as a recurrent network, because with a recurrent network you can have little sub-networks that implement NAND gates and AND gates, and from there you can build a CPU. So this laptop is just a very sparsely connected recurrent neural network. With these recurrent networks you have usually much denser connections than in this laptop, and usually everything is differentiable, which means that you can, through a complex system like that, which receives not only stationary inputs, but entire sequences of inputs, such as speech signals or videos or so, you can then compute a derivative with respect to what to the error of this sequence processor, with respect to the programs that are running on the sequence processor, to the weights. The weight matrix of a recurrent network is the program. You are trying to solve a problem that somehow takes the incoming signal and translates it into some meaningful output. For example, a speech signal comes in, and you want to have a classification of the speech signal that comes in. Then, there's a difference between what should have come out on your training example, because in the beginning all these connections are totally random, but then after some time of training, you minimize, through changing these connection strengths, you minimize the difference between what should have come out and what really came out. So that is again great insight. Now it turned out that if you have deep networks and networks where you want to process long, temporally extended signals, like speech, where you get 100 new input vectors per second from the microphone, for example, then traditional backpropagation in the traditional networks fails, it doesn't work. And the guy who really figured that out was, in my first deep learning project ever, my first student ever, Sepp Hochreiter, 1991, in his diploma thesis, 1991. That's how our whole deep learning research kind of started. So there he showed that as you are getting deep networks, or networks which are recurrent, where you have as many layers in these unfolded networks as there are time steps in the sequence that you're processing, as you're propagating these errors back in time, they get smaller and smaller and they vanish. They vanish very quickly, exponentially quickly. And that's why you can't learn on the standard networks. And then this was overcome. The first way I overcame that was unsupervised pre-training. 1991, a method published back then in Neural Computation, where the idea was, well, okay, let's take these long sequences and let's learn to compress them such that they become short sequences, such that you have a very compressed representation of the sequence, which you can much easier classify. And that's how I then came up with a hierarchy of recurrent networks, and it was a deep learning system, very deep learning, in the sense that it could not only deal with, say, 10 layers, like what Jürgen did in the 60s when I was a baby, but with hundreds and even more than 1,000 layers. And there suddenly we could start to solve all kinds of deep learning tasks that were not solvable before. So the difference between what we did and what Jürgen did, even many decades before we started that, we just were able to go much deeper. And then it turned out this unsupervised pre-training isn't really so necessary, because there is a supervised way of dealing with this problem, which is the long short-term memory. Does anybody know? Has anybody heard of the long short-term memory? No? Has anybody not heard of the long short-term memory? Okay. So the long short-term memory is a particular recurrent neural network which was introduced in the early 1990s, first peer-reviewed publication in 1997, Sepp Hochwald, the first author. And what is the trick there? Why does it work? Why can you deal with thousands of time steps and really, really deep problems with an LSTM network where you cannot deal with such problems with a standard network? Well, there's a stupid little trick. In each LSTM unit, there is a central unit which is just a linear thing, just computes the weighted sum of what's coming in, and there's a recurrent connection from that unit to itself. And it's 1.0, and the activation function of this unit is just the identity activation function, which means that the first derivative of this function is always 1.0. And as you're propagating errors back along these recurrent connections, they don't change. They don't change because you always multiply by 1.0. Now, with a system like that, you can propagate errors not only back 10 steps, you can propagate them back hundreds and thousands and millions of steps. However, to deal with the non-linear aspects of sequence processing, if you want to do interesting sequence processing, you need lots of non-linear steps. So you surround these linear units with a bunch of highly non-linear things, multiplicative units, gates as we call them, and then these clouds of non-linear units, they can take the error signals coming through these linear units, and they get propagated far back in time, and they can use them to rely on a reasonable, to change their own weights and to rely on reasonable things in sequence processing. Now, you may not know it, but most of you have an LSTM like that in your pocket, because all your smartphones have direct access to an LSTM, to a long short-term memory, because Google Voice, since middle of 2015, is using LSTM. Before that, they used something else for doing the speech recognition. So whenever you don't want to type, but you speak into it, using the little microphone icon in the Google questionnaire, then before 2015, they used something, traditional speech recognition combined with a deep network, a forward network, but they replaced that in around August 2015 by a long short-term memory network, which was trained by a method called connectionist temporal classification, which we published in 2006 in ICML, and first author Alex Graves, my other PhD student and postdoc then, and that improved speech recognition not only by 5%, which would have been great, or by 10%, which would have been fantastic, but it made speech recognition better by almost 49%, almost 50%. A huge jump. And now in a noisy restaurant, you speak into your phone, and it understands pretty well what you're saying. It's much better than it used to be. A long short-term memory, which is such a universal, general purpose deep learning method that can be used for all kinds of things. In speech, you have 100 input vectors per second coming in, so every 10 milliseconds a new thing comes in. In language translation, that's a little bit different. There you have letters coming in, or words, and then, for example, you can just train your LSTM system, which in the beginning knows nothing about language, to translate from one language into another. So, for example, you train it by lots of examples from the European Parliament. You have example of English texts, and of French texts. And then the network knows nothing. But you feed word by word these letters into the LSTM, tick, 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 through the recurrent connections. The old stuff is still circling around, so as new things are coming in, the old things are still circling around somehow. And then you ask the network to come up with a string of symbols which corresponds to the French translation. But it knows nothing. So there's a difference between what it should have done and what it did. And you minimize that difference by propagating these errors through the LSTM architecture. And as you do that, it learns the structure of English, the syntax of French, how to go from the meaning in an English sentence to the equivalent meaning in a French sentence. And that's currently the best machine translation systems have at their core such an LSTM. So that's the same thing that works best for speech recognition. Best speech recognizer is also the best thing for machine translation, which is on a different level. And the same thing can also be used to predict the stock market. Here I have a couple of applications. The world's most valuable companies are using LSTM like crazy now. For example, Microsoft is using it for translating text into speech. Google Voice I mentioned. Photoreal talking heads, Microsoft. Apple is using LSTM now to improve its operating system. Lots of other applications. Chatbots are trained by LSTM. Recently, LSTM was used to write the script of a movie, Sunscreen. Maybe you have seen that. If not, you haven't missed much. LSTM is such a universal general purpose computer that can be trained to do lots of interesting real-world tasks, and it was financed by Swiss taxpayers. So although the most visible applications are due to the largest American and Chinese companies, so the main competitors of the American companies, such as Google and Amazon and Facebook, are all in China. And their names are Alibaba, and Tencent is roughly as big as Facebook. And in many ways, some actually advanced because they also do payments and all kinds of things all through one app. And Alibaba for Amazon, of course, and Baidu for Google. So the only large companies who are competitors of the major American companies are Chinese. But all of them are using LSTM for all kinds of applications, subsidized by the Swiss taxpayer. Before I came here, I thought this is going to be just a little tech talk and there won't be much of an audience, but you are actually a large audience by my standards. The other day I gave a talk and there was just one single person sitting in the audience. I said, and it was a young lady, so I said, young lady, it's very embarrassing, but apparently today I'm going to give this talk just to you. And she said, okay, but please hurry. I am the next speaker. The other thing that my lab in Switzerland did, which was not as fundamental as this LSTM and the recurrent stuff, was very practical, however. We took something which is called a deep convolutional network, or actually just a convolutional network, which also has its roots in the 70s. So the guy who invented these convolutional architectures was a Japanese guy called Fukushima. In 1979, he published something which was back then called a neocognitron, but today often it's called a convolutional network, and CNN, and there you have a convolving layer followed by a downsampling layer, and then a convolution layer, and a downsampling layer, convolution layer, and so on. And he trained that in an unsupervised way. And then people such as, well, the first guy was Weibel in 1987. They took convolutional architectures, and back then Weibel called that not CNN, but a TDNN, and did one-dimensional convolution basically, and trained the whole thing by background, which was not used by Fukushima himself. Fukushima used his own learning algorithms and instead what everybody is using today, is used just linear inverse backpropagation of 1970 to train these systems. And then 1989, LeCun and colleagues, they were able to train in a good way two-dimensional CNNs, and basically the architecture introduced by Fukushima, and then use backpropagation to adjust these weights. And then, even back then, you could already do interesting tasks such as handwriting, handwritten digit recognition to a certain extent, and lots of people improved the system. What was done mainly under the leadership of Dan Girija in my lab since 2010 was to make all of that stuff really fast on GPUs. GPUs are graphics processors, and they were invented mostly for the video game industry. And you have 1,024 processors working in parallel. And what do they do? Well, they are used to model, as you are playing video games, to compute the changes you want to see on the screen as you are moving through a simulated world in an ego shooter game or something. And to do that, all the time you have to do vector multiplications, matrix multiplications. That's exactly what you also have to do for the neural network. So all the time you have to do vector multiplications. How much more time do I have? I have only 10 minutes left. Okay. So then this became really fast through the work of Dan Girija, and then in 2011, for the first time, we were able to win competitions with that stuff. And in 2011, that was actually the first time that anybody had a superhuman performance on a computer vision task in a control contest, mainly traffic sign recognition. There was this competition in Silicon Valley, and then our team was able to win that, and it won it in a very impressive way, because the second best guys was, so the third best entry was a machine learning competitor from New York University, and they were about 3 times worse in terms of error rate than our entry. And the second best entry was humans, and they were about twice as bad. So even back then, we already were able to do, in limited domains, superhuman pattern recognition, and now 5 years later, computing became again 10 times cheaper. We can do 10 times as much for the same price. In another 25 years, 100 years after Zuse, we will have another factor of 25, of 10 to the 5, 100,000, and then a big network of today, for example, a big LSTM network today, that has maybe 1 billion connections. Your brain has 100,000 billion connections. So for the same price of an LSTM, a large LSTM today, in 25 years, you will have a brain-size LSTM, which is as big as a human brain in terms of parameters and connections, and lots of superhuman pattern recognition performances you can expect from that. All of that is important for self-driving cars, of course. Some people think self-driving cars were invented by Google, which is nonsense. The pioneer of self-driving cars was Ernst Dickmanns in 1994. He already had self-driving cars on the highway with a safety driver on board, with a red button, just also for legal reasons, but often for hundreds of kilometers, going completely autonomously, tracking up to 5 cars in front of the vehicle, 5 cars behind the vehicle, automatically passing other cars with 180 kilometers per hour, 3 times faster than the Google cars today, and Sigma. But back then, pattern recognition and traffic sign recognition and trolley recognition and all this stuff, which is important in cities, for example, did not work as well as it did today. And so there was still a lot, and there is still room for improvement in self-driving cars. The same techniques which allow us to recognize traffic signs can also easily be used for medical applications. That's a brain scan. Let me take this one here instead. This is from a competition in 2012 that we won. That was the first time somebody was able to win using deep learning, to win a medical imaging competition. And And what you see here is slices of female breasts. And there you see all kinds of cells in the microscopy images, and some of them are mitosis cells, pre-cancer stage cells. And to detect them, you need a trained histologist. And it takes a long time to look at a large image like that and find the mitosis cells. And I'm not able to do it, but I can train my neural network to imitate the histologist who knows what he's doing. And that's how the system then became better than all the competition from MIT, Harvard, and companies who are so super interested in that. Why is everybody? So now, today, lots of startups are focusing just on that. In 2013, we were able to because the promise is so important, they had a grand challenge, the Mikai grand challenge with that. Same team was able to win that. The many startups today are motivated, of course, by the fact that 10% of the GDP of the world is healthcare. 80 trillion is the GDP of the world. 10% of that is about 8 trillion. Now, at least 10%, probably more, at least 10% is for medical diagnosis, where you need all kinds of pattern recognition and stuff like that. Which means that the market for that by itself is about 800 billion per year. 800 billion per year. Apart from that, lots of people in poor countries, developing countries, who at the moment don't have access at all to decent healthcare, through networks like that, will be able to receive at least much better treatments than today. Here's something that Google did with our stuff. So here you see an image, and down there you see a text. Now this was all mainly generated because an LSTM combined with a CNN learned from lots of training examples of images and texts to write captions of text. So there's a CNN which sees the image, creates an internal representation of the image as a number vector, and that goes into an LSTM, a recurrent network, which rolls it out into a text. Here you see a herd of elephants walking across a dry grass field. And you look at the image, yes, it's true. Sometimes it's not quite true. For example, up here it says, 2 dogs play in the grass. But you look closely and you see 3 dogs playing in the grass. But it's not mission critical. It's not like controlling nuclear power plants. And it's getting better and better all the time. Every 10 years we are getting a factor of 100. In 30 years we are getting a factor of 1,000,000. In the near future, for the first time, we will have rather cheap computers that can compute as much as a human brain. If the trend doesn't break, only 50 years later, for the same price, we will have cheap computers that can compute as much as all 10 billion brains of all of humankind together. Everything is going to change. These things will be in many, many ways superhuman. We were able to build the first really deep networks in around May 2015, deep deep networks, because we applied the LSTM principle to deep networks, and we call that highway networks. And the first author on that one is Rupesh Srivastava, who is currently still at the Swiss AI Lab, where much of that has been done. And for the first time we were able to have networks with hundreds of layers. And a very similar thing was then used by Microsoft a couple of months later to win the ImageNet competition. They call it the ResNet, but it's formally equivalent to the highway networks. There's lots of stuff. I could mention application to robotics. A lot of attention recently was devoted to systems which are not just pattern recognizers, but reinforcement learning. It's a traditional way of reinforcement learning, a limited way of reinforcement learning, where you don't have a teacher who tells you what to do next, but where the network itself finds out by playing lots of games against itself to become a better player. This is the first time that a significant achievement like that was done was in 1994, when at IBM, a backgammon learner, a neural network, which without a teacher, just by playing against itself, figured out how to learn to play backgammon as good as well as the best human players. And then Go recently was treated in a very similar way with a couple of extra things, but basically the traditional type of reinforcement learning. And I was proud, of course, because the DeepMind, which did that stuff, was heavily influenced by my students who got to know each other in Lugano. So Maybe you have heard that DeepMind was bought by Google for $600 million roughly, and they're doing machine learning and artificial intelligence. And the first two guys at DeepMind who really had PhDs in artificial intelligence and machine learning, they met in my lab. One of them was Shane Legg, the other one was Dan Biester. Up there you see the subtle smile of Shane right after he sold his company for $600 million. And Dan was the first employee, so two of the first four guys there were from my lab. There were two other guys who were not from my lab. There was Mustafa Suleiman, who was a business developer, and the frontman, Demis Hassabis, who was a biologist and neuroscientist, did important work there. Now later, Alex Graves, who I already mentioned, my former postdoc and PhD student, also joined DeepMind, and Tom Schauer, who also did great work in reinforcement learning. But yeah, so what you really want to do is not just this pattern recognition stuff, you really want to solve general problems through AI, which acts, perceives, and maximizes the future expected reward until the end of your lifetime. I'm getting a sign that I'm in the last hour of my presentation. And then around 2012, we were for the first time able to have, without a teacher, a recurrent network that learned to drive video game cars, play video games in situations which are more complicated than the board game situations, because in the board game situations, all you need to know about the world is this little board position at the moment, and this is not the case in the real world, where you don't see what's happening behind you. All the history of previous perceptions and so on is really important to realize what's the current state of the world and how can I translate that history of perceptions into action sequences that maximize success. And to achieve that, what you really need to build a general purpose AI, you need two things. You need, on the one hand, a controller which takes all these inputs, the pain signals, the reward signals, the vision signals, the auditory signals, and everything, and feeds that into a recurrent network, a general purpose computer, universal computing machine basically, which translates that into motoric output actions that lead to effects. Now you have a separate recurrent network, probably an LSTM or something similar, which learns to take the entire history of all observations ever and all actions ever perceived and learns to predict what's going to happen next. So a model of the world, a predictive model of the world, and is trying to compress the history, trying to extract the regularities, the predictable things among the many things which are maybe not so predictable, and tries to compactly represent those. And then the controller can use that stuff to, can use the knowledge, the algorithmic knowledge of the world model to learn new skills faster. And we started that also in 1991, but now it's becoming much better. Well, already 10 years ago, Alexander Joy Förster won the RoboCup in the Fast League. He was the team leader of that team, where you have little robots and also have world models on board. Let me just mention that the central question, one of the central questions is here. Now you have one module, a recurrent network, which generates the actions, in other words, the experiments that lead to the data. And now, on the other side, there's the model, which learns to predict better and find new regularities in the observation sequences. In the beginning, the model is totally stupid, knows nothing, so you have to motivate the controller to come up with experiments that lead to data where the model can discover something that it didn't know yet. Artificial curiosity. And there's a very simple way of building that stuff. And I won't go into the details because I have only 20 minutes left. And so let me just mention this buzzword that I have there, the formal theory of fun. You Google for that, you're coming immediately out in our web pages which tell you how to implement artificial curiosity like that for general purpose agents. Now, I think in the next thing, in the not so distant future, I believe for the first time we will have animal-like AIs. We don't have that yet. But I think with systems like the one that I just showed you, we will be able to build something like AIs with the intelligence of a little crow, which learns to use tools and can do many things that our best robots cannot do. And then the next step towards human level intelligence may not be that huge. Why? Because it took billions of years to evolve a little monkey, but then on top of that, just a few tens of millions of years to evolve a human level intelligence on top of that. So we will, after that, it will be much, much faster. We have a company that is trying to make that reality. It's pronounced RNNaissance, like birth, because it's about the birth of a neural network-based artificial intelligence. Makes sense? And now do I still have time for this amazing pattern that I found, the amazing pattern in the history of the universe, which seems to suggest that it's history as we know it, human-dominated history is going to converge in the year 2050. Do I still have time for that? Has anybody heard of a concept called singularity? Yeah. Okay. So in the 50s, Stanislav Ulam, a mathematician, he noticed that technological progress is faster and faster, and then he thought, okay, if it's exponentially accelerating, then it must converge in finite time, and that's what he called the technological singularity. Then Werner Vinci, a mathematician from San Diego, popularized that concept in science fiction novels in the 1980s, and that's how I learned about it. And most of the proponents of that idea, they focus on recent events, and they take, for example, Moore's law, and computers get cheaper and cheaper and all of that stuff. But there's a much older pattern I discovered in 2014, which reaches back to the beginning of the universe, and I want to show how beautiful that is. So the whole thing starts across to 13.8 billion years ago with the Big Bang, and now we will see by extrapolation that apparently it's going to converge in the year 2050, which I call Omega. Omega because already 100 years ago, Teilhard de Chardin used the word Omega of this next level that humankind will reach. And Omega also sounds much better than singularity. It sounds a little bit like, oh my God. And now look at this nice pattern. We start 13.8 billion years ago. We take a quarter of that time interval, and from now on it will always be a quarter of that time. And we end exactly at the next big, huge step forward from a human perspective. So this is the history of the world from a human perspective, from the most important events through human eyes. Now, 3.5 billion years ago, that was the invention of life. And you take a quarter of that time, about 900 million years ago, and that was the invention of animal-like, mobile life. And you take a quarter of that time, 210 million years ago, and that was exactly the invention of your ancestors, of the first mammals. And we take a quarter of 220 million years, and that was 55 million years ago, exactly the first primates. And we take a quarter of the time, and it was 13.5 million years ago, exactly the first hominids, your ancestors. And I don't know why it keeps hitting these quarter points so exactly, but it does. Now we take a quarter of the time, 3.5 million years ago, only millions, not billions, million years ago, the dawn of technology, as nature called it, the first stone tools. And we take a quarter of the time. And the next great breakthrough, 800,000 years ago, invention of controlled fire. And we take a quarter of that time, 210,000 years ago, and it was exactly modern man. Your ancestors, people like you and me, and we take a quarter of that time, 50,000 years ago, behaviorally modern man, as he is called, emerging from Africa and colonizing the world. And we take a quarter of that time, 13,000 years ago, the beginning of the Neolithic revolution, agriculture, domestication of the animals. I take a quarter of that time, and it's the first population explosion of the Iron Age, around 3,300 years ago, and which culminates then the ancient world. And then we take a quarter of that time. Omega, 2050, minus 800 years. That's the invention of this combination of fire and gunpowder, and fire and iron in form of cannons and gunpowder and stuff in China. And the world is based on Chinese inventions. The Western world is based on Chinese inventions, like printing and paper during Roman time and gunpowder and so on. And we never paid them a license fee. And we take a quarter of the time, Omega, minus 200 years, and that's the onset of the second population explosion, Industrial Revolution, 1850 roughly, and we take a quarter of the time, And that's the year 2000, with the digital nervous system, PCs for everybody, cell phones for everybody, information revolution, if you will, and everything else is in the future. But it's clear, the next thing might be something in the 2030s, maybe when for the first time we will have human competitive AIs, and of course it's going to get more and more rapid. There you end. And of course these guys will realize, once they are much smarter than we are, because even we can realize that most of the resources in the solar system are not in this thin film of biosphere around the third planet. No, they're out there. Less than 1 billionth of the sunlight hits the Earth. The rest gets wasted at the moment. It's not going to stay like that. They will build billions and trillions of self-replicating robot factories, and they will cover the entire galaxy within just a few millions of years with senders and receivers, such that they can travel the way AIs are supposed to travel, namely by radio from senders to receivers. Everything is going to change. It's a great privilege to live at a time where we see the beginnings of that. This is much more than another industrial revolution. This goes beyond, transcends humankind. It's a step comparable to 3.5 billion years ago when life was invented. And it's a privilege to witness these things. The universe wants to make its next step towards higher complexity, and we are part of that. And that's a good thing. Let's embrace it. Thank you for your attention.